Now let's look at the Carb theorem again. The Carb theorem basically formulates a relationship between consistency, availability, and partition tolerance, hence the name Carb theorem. And it says that all satisfaction of all three of these in any given time instance is impossible. So if you've got a distributed scheme where there are many nodes and each node contains replicas of or partitions of the data, then you cannot have all three properties given any specific time instance. Consistency. Consistency means that all replicas contain the same version of data. So why is it impossible to achieve all of this at all times? Because it may happen that we've written some new data, and before that new data was replicated to the other branches, you've got some read request. Okay? So having to making a system available at all times and making it consistent at all times are conflicting goals for us. Availability here suggests that the system remains operational on all of the nodes all of the time. So there are no failing nodes and there is no time or no one node that denies request to a client. A client can always read and write data. So again, if we need to make data consistent, we'll have to pause the availability and make sure that data is replicated. And if we need to make it available, then we'll have to have some form of a compromise on consistency. Partition tolerance says that there should be multiple entry points. Multiple entry points again affect the consistency. System remains operational on even when the system is split in terms of communication and malfunction. So system remains operational when communication is affected or there is some malfunction regarding to communication. That's again something that directly affects the availability, and the system works well across physical network partitions. If we have many of these physical network partitions, we would be having some trade-off between consistency. So that's what the Carb theorem says. It says that it is almost impossible to satisfy all three of these properties all of the time. So we need to have some form of a trade-off between these. So summarizing what we just said, you can't have all three of these properties. Any two, however, can be achieved. Okay? To scale out, you have to partition. And partition leaves consistency a little lower than required, or it can have effect on availability because a lot of communication channels would need to be open. So in almost all cases, you choose availability on consistency. What we do is we create multiple servers and make sure that our users have access to data at all times. And if there is any issue of consistency, that is handled separately. So looking at availability, availability says that the server is available for all of the time, 99.999%, but that's a little unrealistic. Okay? So for large node systems, at almost any point in time, there's a good chance that there is at least one node that's down. You can't have all physical nodes working at all time. And objective kya hai? What we want is a system that is resilient to such network disruptions. अगर एक node खराब हो जाए तो हमारे पास उसका कोई backup इस तरह का हो कि हम zero time में या no time में clients को दोबारा से service देना शुरू कर दें. And what does consistency says? It says that visibility and order of updates should be such that at the client node, we see no discrepancy in data. Okay? For example, agar row X is replicated on MNN and a client row writes or changes X on one of the nodes, then in the same amount of time or in the same instance, if another client reads that X from M, ठीक है? तो दो नोड्स पे डाटा पड़ा है, एक M पे और N पे, और एक क्लाइंट ने उसी डाटा को यहाँ पे रीड किया है और दूसरे क्लाइंट ने उसी डाटा को यहाँ पे राइट कराया है. तो फिर क्या होगा? अब हमारे पास एक साइड पे राइट ऑपरेशन हो रहा है और एक साइड पे रीड ऑपरेशन हो रहा है, and that would give us a consistency problem. And here is where we need to perform some sort of a trade-off. Maybe we should lock one side while the other is being updated. So that's what Cap theorem states, that strict consistency cannot be achieved if we have availability at all times. So we actually hope for eventual consistency instead of strict consistency. When no update occurs for a long period of time, eventually all updates would propagate through the system and the nodes will be consistent. So हम क्या कहते हैं कि हर वक्त consistency 100% होना possible नहीं है, लेकिन eventually या at the end of the day हमारा system एक consistent state में चला जाएगा. Given the accepted update and given the node, eventually either the update reaches the node or the node is removed from the service. ठीक है, तो data will be propagated or updated to all of the nodes that are connected. And this principle is known as basically available, soft state, and eventual consistency, as opposed to the asset properties that are in relational databases. So in RDBMS, we have atomicity, consistency, isolation, and durability, where in NoSQLs, we suggest basically available, soft state, and eventually consistent. Some of the major points in where NoSQL differs from RDBMS are the looser schema definitions. The documents or key values do not follow one strict definition as a table does in RDBMS. Applications deal with individual documents or data instead of the complete database. Applications are aware of the schema definition as opposed to only the data. And the best thing is that these are designed to handle distribution. So the best part is that these are created in a way that these easily support distribution or scale. Some of the trade-offs are there that no strong support for ad hoc queries, as we see in the RDBMS. And then the relaxation of asset properties, again, is something that NoSQLs possess, where NoSQLs do not possess, where RDBMS had it. One of the major disadvantages is the removal of joins and the group by, order by clauses. This is something you cannot do with a traditional NoSQL database. There have been cases in which, such as MongoDB, they have introduced joins, but in the initial scheme of events, NoSQLs did not support joins or any groups of any kind. So summarizing today's lecture, I'd like to focus on one thing, that more social networking sites we have, the more there is need for NoSQL data stores. And these NoSQL data stores have the ability to store huge amount of data, which is something we could not even imagine while we had RDBMS solutions. And opposed to RDBMS solutions, we do not have RDBMS solutions suggest that everything should look similar. And that's something that NoSQL does not force. So that's again a very good or benefit to us.